Okay, I believe recording has started. I think it is connected, like microphone is connected and we are pretty much good. Um, let's start the session now. Hello everyone, welcome to another lecture of mathematics for machine learning for foundations of AI. And I believe this is our third lecture. In the previous lecture, we have talked about how we can see a given system of linear equations, how we can solve the system of linear equations using different methodologies. We have seen row picture, column picture, and also Gaussian elimination. We have talked about it. Now, in this lecture, we are going to talk in detail about one topic, which is factorization. A is equals to LU. And before that, there are few things which I wanted to discuss before we go further, before we move further. And these are related to our previous lecture. So we have talked, I'm sharing my screen. Yep. So we have talked about inverses, right? So in inverses, let me just come here. In inverses, we have seen, I have my pen down, so the lecture is going to be amazing. Okay. Okay. Yeah, so in inverses, we have seen what is the meaning of a inverse. Let's say I have a matrix A and I'm doing some transformation, right? And this transformation can be like adding something, subtracting something, or multiplying, whatever, right? I have a matrix A and I'm doing some operations on it, and the matrix A has changed from state 1 to state 2. Let's say this matrix, the like after doing operations and all that, let's assume that our matrix has reached to some state, let's say J. Okay, so to go back from state J back to the original state, we call this path. If we are able to go back, then we will tell that the given matrix has a inverse, right? So if you consider that this particular path, right, moving from A to J is one path, then the reverse of exact that matrix, original matrix, is known as the inverse of the given matrix. So here, the opposite path coming from J to A, right? Whatever the things which we are doing, that thing will known as the inverse of the given matrix. I hope you are very clear with the inverses, the concept of inverses, and how do we find inverse. So here we have talked about like what are the conditions to find inverses and the actual meaning of inverses and all. Now let's talk about two matrices. Okay, so we know that how we can find the inverse of but one particular matrix. Now let us consider that, for example, we have two matrices A and B. Okay, so how can we find the inverse of this given matrix? That is the question, and that is the first mini teeny tiny concept that we'll be focusing on. And after that, we'll talk a little bit about transpose. Then we will see uh, the main like heart of the topic, which is factorization. A is equals to LU. Okay, so talking about how we can find the inverse of the matrices, like two matrices which are multiplying with each other. How can we find that? The thing is, it's very simple, right? Here, to find inverse of the given matrix A and B, which are getting multiplied, you just have to multiply with the like reverse order of their inverses. For example, let's say we have matrix A and it does have an inverse, right? We have a associated inverse with it, A inverse. Now, we have another matrix. Let us assume that for this matrix also, we have inverse, which is B inverse, okay? Now, let's assume that you know the inverses of A and B. You know exactly that for this given matrix, the inverse is A inverse. For this given B, the inverse is B inverse. You know exactly, but you don't know what will be the inverse if you multiply these two. The solution, the simple thing to find inverse is that, like, we know that what is the rule? What is the rule of inverse? The main core rule of inverse of a matrix is that if you multiply a matrix with its inverse, then you will get I. And what is this A inverse? A inverse is the reversal path, or you can say opposite order of A, right? If A is going in this order, then the opposite order will be the inverse of the given matrix. Now, similarly, if A, B is a matrix, then what will be the inverse of this? Can I write that B inverse and A inverse will be the inverse of this matrix AB? Because like I hope you have remember the rule of commutative law, I believe, right? I think I'm taking the right name. It tells that, let's say I have a matrix E1, E2 and E3. I'm multiplying it. I can do multiplication with E2, E3 first, or I can do E1, E2 first, right? It doesn't matter what order you are like multiplying, like with whom you're multiplying, whether you're taking e1 e2 first or e2 e3 first, it doesn't matter until and unless you're not changing the positions of multiplication, right? That thing is known as commutative law, right? I believe so. I'm taking a correct name, right? Now here you can see that if you multiply b and b inverse, it will give you I. Okay, so here if you consider from this, according to this law, I can write the given equation as B inverse and A inverse. Okay, and this thing will give me I. So can I write that A, I and A inverse? And again, this thing will also give me, if you multiply a matrix with I, it will give me the same thing. So here, can I write this thing as A, because A multiplied with I will give me A only, and then A inverse. So from this, I'm getting I. So can I tell, right? I know this is the rule, this is the law of inverses, that if you take a inverse of a particular matrix and multiply it, you will get identity matrix. And if I consider, if I'm assuming, like let me change the pen now, if I'm assuming that here this particular thing is the inverse, then it should give me identity matrix. And from my steps, I have proved, I have shown that the given B inverse and A inverse is giving the identity matrix. If they are giving the identity matrix, can I say that this particular thing, right, B inverse and A inverse are the inverse of AB? So from this, I have figured out key how I can find the inverse of the given matrix. Very clear. I hope you have understood. So if someone asks you that, okay, Jabir, like let me change back to black ink, okay? If someone asks you the question, like here's the question, right? If someone asks you that, okay, I have a matrix A, they have given that the matrix A has inverse, and they have also given that matrix B is also having an inverse. Now they like in question they have asked, find the inverse of AB. All you have to do is that we know B inverse, we know A inverse. Just multiply these two, and whatever the answer you get, that will be the inverse of AB. I hope you have understood. Very simple concept. Now let's move to the next concept here, which is transpose. What is the meaning of transpose, and how we can like represent it mathematically? Okay, so here talking about transposes again, like in few minutes I'll talk about transposes in detail. Uh, we'll see different properties of transposes, and when we talk about transpose, we will talk about one important concept, which is symmetric matrices, which is really important in machine learning and applied mathematics. But let's have a very like nuanced understanding of what is the meaning like of transpose, right? So here, let's say I have a matrix A. Okay, now uh, I'm taking example 1, 2, 3, 4. Now the definition of transpose is that you convert rows into columns and columns into rows. Basically, let's say this is a row 1, right? This is my row 2. What you have to do is make row 1 as column 1 and make row 2 as column 2. Basically, swap the or interchange the rows and columns, right? So what the A transpose will look like is this, something like this. So 1, 2 and 3, 4. What is happening here, right? The definition of transpose is that you're like interchanging rows into columns and columns into rows. So this is my row 1, this is my row 2. Now what happens is that the row 1 will become column 1, the row 2 will become column 2. This is the simple definition of a transpose. Now, how I can represent this mathematically? Okay, so can I write that for the given matrix, let's say A, which has n elements, and each element is being represented with a representation of A of ij, then the A transpose will be a matrix which will have again n elements, and the representation of this would be A of ji. This is the mathematical description of a transpose. Okay, you can take this as an example, right? So I have let's say a11, a12, a21, a22. Okay, I hope I'm writing columns right. Okay, yep. Now, all we have to do is to find transpose, we have to change rows into columns and columns into rows. So here, what we'll do is that you have A11, right? You will just swap, like you will swap the elements. So here, you will take in the place of 1, you will just write here I, j, and same. So it will be the same. But what will happen is that this will come here, right? In the place of I will have j. So here A21 and again A12, A22. So this will be the transpose of the given matrix. So I hope I have understood actual definition, example, and mathematical description as well. Now, we are talking about inverses. So let's stick to that. Now, my question is again, let's talk about question. I have, let's say, uh, I have a matrix A, right? And I know the transpose of A. Okay. My question is, what will be the inverse of A transpose? How can I find the inverse of A transpose if I know A and its transpose? Okay, let's talk about that. Okay, let me write it with blue pen. What is the law? What is the rule of inverse? The rule of inverse says that if I have a matrix A, okay, and let's assume that it has a transpose, right? If it does has a transpose, sorry, inverse, my bad. If it does has an inverse, then if I multiply it inverse, it will give me I. Now, what is the main goal of mine? My main goal is to find the inverse of A transpose. So can I put transpose on both sides? Can I transpose the matrix on both sides? I can do that, right? So here we know that I transpose will give me I. Okay, so this will give me I only. Now, if you remember, there is a law which we have studied in school, which is transpose reversal rule, which says that if you put, let's say I have AB and I have put transpose on that, then the resultant answer would be B transpose and A transpose. Okay, so here if I put transpose on this entire thing, then the resultant would be A inverse transpose and A transpose is equals to this. Now I want you guys to observe this equation. If you observe this equation, you will realize that A inverse of T and AT is equals to I, right? So can I tell that the inverse of AT is this? Okay, so this particular thing which I'm circling right now, right? This tells me that the inverse of A transpose is equals to, if you know the inverse of that particular matrix, just transpose it and it will give you the inverse. Simple, very easy to understand. I hope you got the point, right? The inverse of A transpose is this. Let me put it with different ink. Green would be good. Yep, green would be good. Yeah, orange. Okay, this is the inverse of the given matrix, right? Transpose of the given matrix. Okay, so I hope you have understood two mini concepts which I wanted to discuss in the previous lecture, which is finding the inverse of multiplication of matrices. If two matrices are getting multiplied, then what will be the inverse? Okay, and the second thing is, if you know the transpose of the matrix, then what will be the inverse of the transpose? I have shown you both of that in mathematically, of course, right? You can take example and try it out. Okay. Now let's come to the heart of our topic, which is A. A is equals to LU. Okay, what is the meaning of this? And let me tell this statement, right? I know this session is a bit of theoretical and Bill Sundays are going great, but this is also important. Okay. A is equals to LU. I'm going to tell a statement and I want you to remember this statement forever. Okay. The statement is that this A is equals to LU is the most fundamental slash basic factorization of a matrix. Okay. Factorization of a given matrix. Okay, so let's assume that you have a matrix and that matrix is a very complex matrix, right? It has thousands of numbers, it has like big entities, large numbers, whatever it might be, right? Yeah, the main thing is that I want you to assume that A is a very complex matrix, whatever your definition of complex, like whether it has a number of rows and columns with big numbers, you can take that as a complex matrix, right? Okay. Now, my A is equals to LU tells me that you can break down the complex matrix into different simple entities, and these entities are L and U. And what are these L and U? Use the upper triangular matrix, which you will get after performing elimination. And L is the lower triangular matrix, which tells exactly, which is like a record book, which tells which, like what exact eliminations has had happened. Everything is going out of head. I know that. Let's take an example. Okay. Let's take one example that before I go into mathematics stuff, I'm thinking of real world example by which you will understand in detail of what is the meaning of LU. Now, I got example. I got example in head that let's say you want to build house, right? You have house. House is very complex, right? You will have a number of different rooms. You have your launch area. You have your like kitchen. Different things, right? Different compartments, different components, different elements of a given house, right? A house has a number of different things. Got it? Now, can I tell that house can be like house does not appear out of blue, right? House does not come out of blue. Like it takes something, some foundational thing, some basic things to build house, right? Can I tell that house involves majorly two things? One is blueprint. Blueprint exactly tells you that where should be the what like bedroom should be like where at which location, kitchen should be at which place, so you know exactly by just looking at the blueprint that you can tell this is where kitchen is, this is where bathroom is, sorry, so you can exactly tell that. Okay, now along with it there are some concrete things. For example, you need cement, you need pillars, you need sand. These are foundational components which are required to build a house. So these are the two things which you really need to build this house. Similarly, if you take matrix A, which is complex matrix, every matrix does not appear in itself. It comes from L, which is the blueprint, and U, which is the resultant you got after elimination. Okay. Okay. Still, we did not understood, but we understood this analogy. Now, let's go back to our first lecture, right? I hope you remember Gaussian elimination. In Gaussian elimination, what we did, right? What we did, that is my main question. And if you tell me this question, I can guarantee you that you'll understand LU factorization. If you notice here, what we did in this example is that we have a matrix A and we keep on doing the elimination process on matrix A until we get U. Okay, so here, can I write that? Let's go to our Gaussian elimination. So in Gaussian elimination, in Gauss elimination, we have like taken a matrix A and we keep on doing elimination steps, E1, E2, whatever, right? You keep on doing elimination steps in between, and you keep on doing the process of eliminations until and unless you get U. Okay, and what is U? U is basically a upper triangular matrix in which all the elements underneath it will be zero. You can see that if you draw a diagonal, then all the elements which are below the diagonal will be zero. So this is my upper triangular matrix. So the thing I'm doing in Gaussian elimination is that I'm taking A and I keep on performing operations until and unless I get U. Okay, let me write U properly. Okay, U. Now, how my question is, okay, Jabir, we have understood that in Gaussian elimination, we are taking a matrix and we keep on doing elimination until and unless we get U. Now, how can I describe this entire process, this entire life cycle mathematically? Okay, can I write? Can I write, let's say, I have a matrix. Let's take a simple example, okay? 1, 2, 8. And 1, 7. I have taken a simple example. Now, what will be the U of this? The U would be 2, 1, 7, and the element below the diagonal should be 0. Okay, so 0. Now, can I write that 2, 8, 1, 7? Right, I'm multiplying with the elimination matrix and it is giving me U. Okay, now what is this E? E is basically an elimination matrix which tells me what operation I'm doing. What operation I'm doing? I'm taking row 2 and in row 2 I'm multiplying with 4, 2 4s are 8, right? Okay, to row 1. Okay, in this what will happen is that my matrix would be 0 and minus 4, 1. This will be my elimination matrix, and again this will give me like 1 minus 3, right? 4, it will be 3 here. Okay, now 2 8 1 7 is equals to 2 1 0 3. Okay, now this is my E, this is my A, and this is my U. Now, can I write, if I take E here, then it will give me A is equals to E inverse U, right? And if you take the inverse of E, E inverse would be the opposite. Basically, the signs only change. So this will give me 1 0 4 1. So here, uh, if I write matrix 2 8 1 7 is equals to 1 4 0 1 and again 2 1 0 3. So this is known as E inverse and This is also known as L. L is nothing but lower triangular matrix, and it tells me exactly uh, what is happening, what transformation is happening. You can see that if you observe this, you will understand that at row 1, at row 2, I'm like subtracting 4 from the main matrix. Okay, I hope you got the point, right? Basically, the journey which describes from A to U is L. Okay, I hope you understood the point. Like this is known as like the least factorization. Now, like let me take a like simple example, right? Let's say I have a 3 by 3 matrix, right? 3 by 3 matrix, and in 3 by 3 matrix, let's say the matrix is A, and I'm getting U by doing some operations. Let's say I'm performing first on row 2, right? So E 2 1. Again, I'm performing, again, I need the third element as well. So E 3 1. After that, again, on pivot element, if you take this, let's say A, B, C, D, E, F, G, H, I. Okay. Now the thing is, I'll take row 1, I'll perform on this 2. I'll take this and I will perform on this, right? Because I want, if this is the pivot, then I want all the elements to be 0. If this is the pivot, then all the elements should under it should be 0. Okay. So here I'm writing that in mathematical form. After that, E 3 2. Okay. Now I'm multiplying with A, it will give me U. Okay. Now the thing is that if I multiply this thing now, right, directly, it will give me so much of complex multiplication. First point. And second, visually, this does not give me any sort of information about the process, any sort of info about the process. Okay, that is why if you take this thing on the right side, you will get opposite order, right? So when matrices go from here to there, you will get opposite order, which is E 2 1 inverse, then E 3 1 inverse, and E 3 2 inverse, right? Totally opposite order, and you multiply it with U, and we know that wait a second, wait a second. I believe I have an example in my uh, book. Okay, I got example, right? So let's assume that our E 3 2 and E 2 1. Okay, I'm just writing this. Now let's say that I'm doing 1 0 0 0 1 0 0 minus 5 1, and I'm multiplying with another elimination matrix 0 0 minus 2 1 0 0 0 1. Just before the lecture I did this. If you multiply this 2, then what will happen is that you will get answer as 1 0 0 minus 2 1 0 10 minus 5 and 1. Okay, so like if you see this matrix, this will tell you that at row 3 we are performing operation from row 2. Like this tells me that in row 3 I'm performing row 3 minus 5 row 2. If you take this, this tells me that at row 2 I'm doing row 2 minus 2 row 1. Okay, so this is giving me perfect information, but what is this giving? Right here I have minus 2 10 and all that. So this is a the if you take 10, 10 is not describing anything. Now if you take the exact inverses, right, if I multiply E 3 2 inverse with E 2 1 inverse, right? I will get 0, 0, 0, 1, 0, 0, 5, 1 and multiply it with 1, 0, 0. The signs will only change in elimination matrix. It is really simple. Like if you have an elimination matrix, then it inverse would be, if you have negative here, then it will be positive. If you have positive, then it will be negative. Okay. Now 1, 0 and 0, 0, 1. Okay. Now if you multiply this, then 10 will not never come here. So 0, 0, minus 2, 1, 0, I believe so. Let me check the answer. Uh, yeah. I think I have to take reverse order, not this order. This will be my first, this will be my second, multiplication order. Okay, and I will get the answer as positive 0, 5, 1. And this will exactly tell what I'm doing. I'm doing subtracting 2, subtracting 5. Right, and 10 is not coming unnecessarily. That is why this particular cluster shows me L. This particular cluster is known as L, and the multiplication will be much easier. Right, it exactly tells me that what operations is being like performed. And if I do this, right, let me draw in red color. Right, if I do this particular thing now, then the loss is that I manually perform a lot of multiplication, right? And the answer I get, this particular whatever the answer matrix I get, right? It does not tells me what is happening. But if you take the inverse, right, the multiplication will be much easier, and the L, like we are calling this particular multiplication as L, right? This L tells you exactly the things which you did on A to get U. So A, let me write it here, that A is equals to LU tells you exactly the thing, right? Let's say you have A, the exact thing which you have to do, the exact elimination steps which you have to do to go at U. L acts as a record book which you just have to follow, right? To get U, as simple as that. That is why uh, A is equals to LU is the most efficient, and in one single step you can find the solutions of a given system of equations. So from now on, if someone is asking you to find solutions of system of equation, then you will use this method, because this is a one single step method, right? And what are the flaws? The flaw where this A is equals to LU will break is when row exchanges happens. Okay, if they are row exchanges, then A is equals to LU will fail. In that, we introduce something called as permutation matrices. Let's talk about that. Permutation matrices. Permutation matrix is that permutation matrix is basically a identity matrix, but swapped with the rows. Swapped the rows based on the requirement. For example, let's say I have A, right? I have A with 0, A, B, C, A, B, C, D, E, F, G, H. Right? Now, we know from Gaussian elimination that the first pivot or any pivot in that sense, right, should not be 0. If you get pivot, then it tells me that to interchange rows, right? Make this as first row, like take any row, make this as first row, because we don't want any we don't want any pivot to be 0, right? So to do that, we take something as permutation matrix. Permutation matrix is, for example, let's say you want to swap row 1 with row 2. What you will do is that you take the matrix, you multiply it with P. And P is basically, let's say we know I, right? 1 0 0 0 1 0 0 0 1, right? Now P would be, if you want to swap row 1 with row 2, then basically swap these two rows in identity matrix. So here 0 1 0 uh, 1 0 0 0 0 1. Take this P, multiply it with A, then you will get a swapped rows of EAB, like here, right? Such that you can ignore pivot. So this is known as permutation matrix. Permutation matrix are used to swap matrix when you get pivot, right? What we will do is that we will just multiply it with P such that the swapping will happen. Now, as I said that the A is equals to LU will, A is equals to LU tells you the most basic factorization. Basically, you're taking a complex matrix, breaking it into two pieces. That is the main idea here. Now, A is equals to LU will fail if there are zero pivots in the element. If they are, if you are performing row exchanges. In that thing, the equation of A is equals to LU will get changed to PA is equals to LU, right? What we will do is that we take the permutation matrix. Permutation matrix shows or tells you exactly what are the rows you have changed. Just multiply it with A and your entire equation will get balanced out. So this is the concept of finding the inverse of multiplication, multiplied matrices, finding the inverse of transpose, and factorization, and and also about permutation matrix. So I hope you have understood four topics. Now let's talk a little bit about transposes. Okay, we know what is a transpose and how to find transpose. So this is the meaning of transpose, and we know how to find transpose and all. And there is one law that you also need to understand about transpose, which is first law is that if you have AB and you are performing transpose, then the resultant would be B transpose A transpose, which is the reverse order. Now, if you know A and A transpose, and for sure you know that A has A inverse, then the inverse of A transpose, the inverse of A transpose would be A inverse and its transpose. Okay, so I hope you got the point, right? To find inverse of a transpose, you just take the inverse and transpose it, and it will be the inverse of the given transpose matrix. Very simple to understand. This is second rule. Now let's talk about one last topic, which is symmetric matrices. Right? Symmetric matrices are the matrices. This is a very important condition, right? Which is if you have A and you know the A transpose, and after swapping the elements rows and columns, you get to know that basically A is equals to A transpose, right? If you get this condition, then you call that particular matrix as a symmetric matrix. Okay, so this is the condition of a symmetric matrix, and let me tell you this here, right? Uh, in applied mathematics, in machine learning, symmetric matrices are the most important matrices, right? Because of their properties, because of the concepts called as orthogonality matrices, eigenvectors, eigenvalues, all these things which we'll be talking in future. But this lecture is going to be the last lecture of elimination, right? From now on, we will move on to a very new topic. You can consider it as the beginning of actual linear algebra. Till now, we have been just brushing up the old concepts. Okay, now, how can you, my question is now, how can we build the symmetric matrix? Right? How can we build a symmetric matrix? That is the question. To build a symmetric matrix, there is a rule. The rule tells me that let me just look into it. I have like written scriptures. Okay, so take any rectangular matrix, right? It doesn't have to be a square, right? If you multiply it by its own transpose, right? If you take any rectangular matrix, let's say I have a rectangular matrix like this, and it doesn't have to be square all the time, right? If you take, let's say this is R, if you multiply it with a transpose, right, rectangular matrix transpose, the resultant you will get, the resultant, let's say, is Z. Z will always be a symmetric matrix. Always be a symmetric matrix. For now, just remember this, okay? Uh, this is the thing, right? I have some other thing in notes, but I don't want to go there. I just want to stop the lecture here. This is a very simple lecture, and to be honest, I made a mess on board, right? I wrote a lot of different things, but let me just summarize it up. What are the things we have studied? First, we have studied how to find inverse of two multiplying matrix, how to find inverse of transpose. After that, we have talked about how you can break a matrix into its factorization, into its most fundamental parts, which is LU, right? And what is the meaning of A is equals to LU? You have the house can be built from the blueprint and some foundational items from foundational elements. Similarly, you have a big matrix. That big matrix comes from LU. L is the record book, which exactly tells that what eliminations you did uh, to get U. Okay, and U is the basic form of that matrix A. Okay, we have understood, and we have understood like how we can find solutions of a given system of linear equations in one step using A is equals to LU. Right, that is the third topic we have talked about. And again, we came back to transposes, and we talked about symmetry of matrices, right? So these are the four concepts. And one more thing is that I have specifically mentioned that A is equals to LU will fail if there are any sort of row exchanges. And to tackle that, we use permutation matrix. What you will do is that you know that, okay, what are the row exchanges I did in order to get U, right? So when you already know the row exchanges that you did, just write them in permutation matrix format and multiply it with A, right? In A is equals to LU, multiply it with A, and automatically it will give you PA is equals to LU, and it will balance the equation. So in that case, if row exchanges are happening, then you will not use E is equals to LU, you will use PA is equals to LU. Understood. So these are the 5 topics which we have talked in this lecture. I'll stop here, and next lecture is my favorite in linear algebra, and it is going to be on vector spaces. So with that being said, I'll stop my screen share, and in vector spaces, we'll talk about what is the actual meaning of vector spaces, column spaces, the most interesting topic in linear algebra. So with that being said, thank you everyone. If you watched till here, it really means to me a lot. I'll provide you the lecture notes, the book which I'm actually following for this series, right? You can also follow it. It is Gilbert's Tank book on linear algebra, right? I'll provide the link on the description. So with that being said, thank you everyone. Thank you for watching. Bye.